So far we have discussed extensively the basis operators, the evolution of the basis operators, which forms the basis for calculating the evolution of the density operator through a given pulse sequence. Now we will just take a summary of all of these time evolutions, and I have listed here a few illustrative evolutions, and by and large we will be using these only. Most of the time we will be using these many equations for calculating the evolution of the basis operators. Here Ikx is supposed to represent the in phase magnetization of the K spin, and it evolves under the influence of the chemical shift Hamiltonian Hz for a time t, and then it gives you Ikx cosine omega kt plus Iky sin omega kt. Iky under the same Hamiltonian for the time t gives you Iky cosine omega kt minus Ikx sin omega kt. Notice here the change in the sign depending upon what your basis operator is. So you have to be careful with regard to what sign you will get here. This I have written for K spin, but it can be for any other spin, L spin, M spin, whatever. So in your density operator expression you may have combination of all of these, and then each one of them will evolve with its own characteristic frequencies as are indicated here. Now Ikx again under the influence of the coupling Hamiltonian for a time t gives you Ikx 4 sin pi jkl t, where jkl is a coupling constant, plus 2 Iky Ilz sin pi jkl t. Here we consider the coupling between the spins k and l, and therefore you have the coupling constant kl here. If it were a coupling of some other spin k to m, then it will have a coupling constant here as jkm, and here it will be accordingly Imz. So therefore depending upon what coupling one is looking at, then you will have such kind of expressions. If you have multiple couplings, then you will have to evolve these stepwise, first under one coupling and second time under the second coupling, but the same equations will be applicable. Each term will have to be evaluated again for another coupling and so on. So Iky under the influence of the coupling jkl, that gives you Iky cosine pi jkl t minus 2 Ikx Ilz sin pi jkl t. Once again notice the change in the sign here. If you are starting with kx, you get plus here, if you are starting with ky, you get a minus here. This is basically due to the convention you have used of a particular kinds of rotation, the sense of rotation in the group. Now if I had, for example, all these were in phase magnetizations of the K spin, we also treated anti-phase magnetization of the K spin. We had the basis operator such as this 2 Ikx Ilz under the influence of the coupling Hamiltonian, it gives you 2 Ikx Ilz cosine pi jkl t plus Iky sin pi jkl t. We do not need to consider a chemical shift evolution because it will be simply similar to what we have here. Wherever there is Ikx evolving, you put this equation, the other things remain the same. So we do not need to explicitly write the chemical shift evolution of such a term. Important thing is the coupling evolution of this. Likewise 2 Iky Ilz under the influence of the Hj Hamiltonian for time t gives you 2 Iky Ilz cosine pi jkl t minus Ikx sin pi jkl t. Once again notice the change in the sign. So in summary, essentially it is these set of equations by and large we will be using for calculating the evolution of density operator and the corresponding basis operators in any given pulse sequence. Therefore it simplifies your calculation quite substantially, and it is important to remember these equations pretty well so that we can easily write the evolution of the density operator through a given pulse sequence. Now, so let us move forward. The next thing to see is when you actually calculated the evolution of the density operator, obviously you will be getting a mixture of various basis operators adding together in the summation. Now we have also seen earlier in the density operator, depending upon what sort of elements that are present there, When you actually make a measurement, some of those ones appear and some of those do not appear. So therefore, when you have such a kind of a situation, we have to ask a question as to among the various basis operators which will form the density operator, which of these are observable and which of them are non-observable. So what we measure is a transverse magnetization, so which is represented as mx plus IMy, that is m plus, and this is called as m plus. This is also called as raising operator or ladder operator, these are called ladder operators, whatever. So this is what we measure, transverse magnetization is what we measure. This is the x component of the magnetization, this is the y component of the magnetization, and this is the complex magnetization we measure. And we have seen earlier that we have to calculate the expectation value of the corresponding operator for such a kind of an observable. If this is our observable, the corresponding operator is I plus, which is Ix plus Iy. So then what we have to do? We have to calculate the trace of this operator with the density operator that you might get at the time of detection. Just before detection, what is the density operator? We have to use the trace of that one. So what we have to calculate for measurement is trace I plus rho, and rho is the density operator just at the time of the detection of your signal. Okay. Now since rho is a summation of various basis operators here, so we will have to calculate trace of the individual basis operators to see what basis operators contribute to observable signal and which ones do not. So that is what is indicated here. So you calculate trace BSI plus, and notice that this actually is quite symmetric. BSI plus is the same as trace I plus BS, it does not matter which order you put them in, and then this should be non-zero for BS to be observable. So this was the condition we have derived earlier. The expectation value has to be non-zero for it to be observable. So this is the condition. So we are going to therefore calculate the traces of these individual basis operators with this I plus operators. Let us take a few examples here. So let us first consider Bs is equal to Ikx. This is the in phase basis operator whose evolution we saw earlier, and a trace of Ik plus Ikx. Okay, now I have taken it for K magnetization here, and if it were a L magnetization you will put L here and so on and so forth. So if it is a sum of various spins, you will have to take the sum of all of those things here and then calculate the trace, but this is enough to demonstrate what sort of things we are going to get for all the individual spins. So Ik plus, if I write here, this is Ikx plus Iky, that is Ik plus, and then I have the Ikx here. So therefore if I make my multiplication here, trace of Ikx square, that is this and this, the first term gives you Ikx square and the second term gives you plus I trace of Iky Ikx. So trace of Iky Ikx. Now how do we calculate this? Since both are operators of the same spin, so what we will do is I will take the individual spin operators here and take a multiplication. So the trace Ikx you know is half 0 1 1 0, and therefore I take a square of this, I get 1 by 4 here, 0 1 1 0 0 1 1 0 plus I trace of 1 by 4, this is Iky, half 0 minus I0 is Iky, and Ikx is again half 0 1 1 0. So therefore trace 1 by 4, 0 minus I0, 0 1 1 0. So what is this one, the trace of this? What is the trace? Trace is the sum of the diagonal elements. So therefore this gives me half, this is 1 plus 1 2, therefore this, the first term gives me half and the second term gives me 0. Therefore this is observable because this is non-zero. Okay. Therefore this term, this basis operator is observable. Let us look at the second one, Iky. So I do the same thing here, Ik plus with Iky. So Ikx plus Iky, and therefore this is I trace Iky square, this one here, Iky square plus trace Ikx Iky, this one here, Ikx Iky, So use the same matrices again here for IKY. I put here 0 minus I0, 0 minus I0, and for this 1 by 4, 0 1 1 0, 0 minus I0, and we take a multiplication of this. So here I get I is here and this gives me 1 by 4, IKY square obviously is 1. So therefore this is 1 0 0 1 plus trace 1 by 4 I0 0 minus I. So this again gives me half, but there is a factor I here, therefore it gives me I by 2, and this one gives me 0. Nonetheless it is non-zero and therefore this is observable. Now let us look at this. This is once again K magnetization, but now it is antiphase with respect to the L spin. So I take this Bs is equal to 2 IKX ILZ. This is antiphase basis operator. Now doing the same trick, so IK plus, here I have 2 IKX ILZ. So therefore I get here 2 trace IKX plus IKY and IKX ILZ is here, and the 2 I have taken it out. So then what I get? So this gives me IKX square ILZ, this remains as it is, and this gives me 2I IKY IKX ILZ. These two are of the same spin and this is of a different spin. Notice here these two are of the same spin and this is of a different spin. Therefore what I have to do to calculate this, I actually have to take the matrix representations of the individual operators here and then take a direct product. So therefore to evaluate this, so I have here 2 trace and this gives me 1 by 8 because there are 3 terms here, half 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 gives me 1 by 8. So then IKX square is 1001 and therefore I have here 1001, and then ILZ is 100 minus 1. This is for a different spin. Notice here, so let me write that so that it becomes clear to you. So this is for the K spin and this is of the L spin. So therefore this is again for the K spin and this is of the L spin. So when I do that, I take a direct product of this and direct product here. So I get here 2 trace 1 by 8, 1 minus 1, 1 minus 1, all other terms are 0, and here I have 2I trace, this gives me minus I minus I, and all other terms are 0. So therefore what we get, if I take the trace, it is the sum of all the diagonal elements, this is 0, and so also it is 0 here, and there the whole thing is 0. So therefore notice this antiphase magnetization here is not observable. 2IKX ILZ is not observable. Similarly, if I take 2IKY ILZ, which is again antiphase basis operator of the K spin, antiphase with respect to L, so I substitute here IKY ILZ, it's the same calculation, and you have IKY ILZ here, so use your 2I trace IKY square ILZ plus true says IKX IKY ILZ. So once again we do the same thing here, and this is for the K spin and this is for the L spin, and here it is again for the K spin and this is for the L spin, and then we take a direct product, of these two matrices. So I get here 1 minus 1, 1 minus 1, and here again I get y minus I minus I, and you see the trace of this is 0 and the trace of this is also 0. Therefore this is non-observable. So therefore I have illustrated here how to calculate whether a particular basis operator is an observable or not. When you have sum of various kinds of operator terms in your density operator, not all of them contribute to your observation. When you make a measurement, some terms will contribute to the measurement and some will not. And those which do not contribute to your measurement, you can simply ignore them so far as your signal is concerned. Now if you do a similar exercise for the various operators representing the double quantum and 0 quantum, then you will find that they are also non-observable. So however, antiphase basis operators evolve under J coupling into observable terms. Now if you are doing an experiment where at the beginning of detection, so you have the antiphase magnetization, and the antiphase magnetization evolves under coupling, as you have seen, evolves under coupling into an in-phase magnetization here. For example, if you took 2 IKX ILZ, it evolves into an IKY term here, and similarly 2 IKY ILZ evolves into an IKX term here. So, after that evolution is done, if you consider evolution during the detection period and during the signal collection, and therefore these terms will then contribute to observable magnetization. These themselves are not observable, but these ones evolve under the coupling into observable magnetization as IKY or IKX. So, therefore, antiphase of basis operators evolve under J coupling into observable terms. Therefore, if you are at the beginning of detection, if you have this antiphase term, and during detection if you do a decoupling of the two spins, then those terms will not be observable. But if you do not decouple, you allow them to evolve during the detection period under the influence of the J coupling, then they will contribute to observable magnetization. Okay. So, we have now prepared the ground for calculating the evolution of the density operator through any given pulse sequence. What we are now going to do is to consider a simple example. The first example, this is the spin echo. This is considered to be one of the most crucial and fundamental pulse sequence which is used in many of the multipulse experiments, and we will now explicitly calculate the evolution of the density operator for this particular pulse sequence, namely the spin echo. Now you recall the previous lectures. What is the spin echo sequence? It starts with a 90° pulse, and then there is a tau period, then you have a 180 pulse here, and again the same tau period, and we said that the magnetization which was decaying here, now it rebuilds and then causes an echo at this point. So, and all the field inhomogeneities will be refocused, chemical shifts will be refocused. This is what we said, and we are now actually going to explicitly calculate that using the density operator formalism. Now notice here these phases I have chosen arbitrarily, they can be anything, you can use X or Y or combination of those, and we will take some illustrations of those as well. We keep, for simplicity, for illustration, we keep the first pulse as 90x, and we have the various time points indicated here. This is time point 1, 2, 3, 4, 5. So, this is the beginning of the detection period. We will do our calculation until this point. We are not going to do a further evolution here. This will be the normal FID and the data collection happens here. So, we will see what is the effect of this pulse sequence until this point. Therefore, we evolve the density operator through these steps and reach up to this point. Okay. So, now we consider two spins K and L and without coupling. Assume to the first case that there is no coupling between the two spins. So, at time point 1, this is rho is rho 1, what is the density operator? It is just the sum of the two IZ operators, right. So, because you remember the equilibrium density operator was the IZ operator, which is the sum of the Z magnetizations of the two spins. So, therefore, this is IKZ plus ILZ. Now, if I apply the 90° X pulse, then I get the density operator at time point 2, this gives me minus IKY plus ILY. So, this is the 90 X pulse. Now, during the next period tau, this evolves under the influence of the chemical shift because there is no coupling. So, we need to consider only chemical shift evolution. So, I consider the evolution of the individual these operators here. So, IKY gives me IKY cosine omega k tau minus IKX sin omega k tau. For ready reference, I also put that here. Those of you who can see, this is a small picture, but this I hope some of you can see it with good eyes. So, we have the x here, the y here, minus x here, minus y here, and this is z. So, there is a rotation around the z, which is the chemical shift evolution. So, the IY goes to cosine omega k tau here. This is this component, and this component will be minus IKX sin omega k tau. Similarly, for the L spin, so this will be minus ILY cosine omega L tau minus ILX sin omega L tau. So, this will be the density operator at the time point 3. Now, what I do at this time point, I apply 180° X pulse to both the spins. So, 180° X pulse, what does it do? this minus remains the same, it shifts IKY to minus IKY, rotates by 180 degrees. So, it is a rotation from here to here. So, is minus IKY cosine omega kt, this remains the same and it has no effect on IKX, and therefore, this remains as IKX sin omega k tau. Similarly, for this ILY goes to minus ILY cosine omega L tau minus ILX sin omega L tau. So, this is the result of 180 degree pulse. Therefore, we now got the density operator at time point 4 in the pulse sequence. So, rearranging those terms, remove the signs, I rewrite this row 4 as IKY cosine omega k tau plus IKX sin omega k tau plus ILY sin omega L tau plus ILX sin omega L tau. So, during the next tau period, I will have to evolve under the chemical shift once more. Again, there is no coupling, therefore, evolve under the chemical shifts only. Now, there will be how many terms? Each one of these produces one term here. So, it evolves under the chemical shift, and so therefore, I will have total of 4 terms. Here also there are 4 terms, each one I will have to evolve under the chemical shift. So, therefore, cosine omega k tau, this remains here. Now, for this IKY I write here IKY cosine omega k tau minus IKX sin omega k tau plus for this term now sin omega k tau, and I have the IKX term here IKX cosine omega k tau plus IKY sin omega k tau. Notice the change in the sign here. So, we have to be careful with that, these are very important. Similarly, now for the L spin, this is cosine omega L tau, the evolves ILY cosine omega L tau minus ILX sin omega L tau, and the ILX term gives you sin omega L tau into ILX cosine omega L tau plus ILY sin omega L tau. These ones are put in different colors. The reason is that these ones will cancel out. See here IKX, what is this product here? Cosine omega k tau sin omega k tau, and here it is sin omega k tau cosine omega k tau, and the same IKX term. Therefore, this will cancel this term, right. So, maybe I can just indicate that to you by explicitly writing that there. So, this will cancel this. Similarly, for the ILY, so this will cancel this one. So, then what we are left with? So, we are left with IKY cosine square omega k tau, and this will give me sin square IKY sin square omega k tau, that is this here, and similarly for ILY cosine square omega L tau plus sin square omega L tau, and obviously this is 1 and this is also 1. Therefore, I got here row 5, this is the density operator at time point 5, this is IKY plus ILY. So, everything has vanished, all these time dependencies has vanished, the frequency dependence has vanished. We started with the density operator row 1 as IKZ ILZ plus IKZ, and after the first 90 degree pulse I had minus IKY plus ILY, and I got back IKY plus ILY. So, the chemical shift evolution has completely been refocused except for the change in the sign here, and that of course will depend upon what of the sign of the 180 degree pulse, and accordingly we could have had a different minus sign here as well. We will also see that later. So, therefore, the chemical shift information is completely refocused. We got back the basic operator as we had in the beginning. Now, let us consider the situation when we have the coupling as well. Now, the coupling means when you have the coupling, your total Hamiltonian will be Hg plus Hj. This is the chemical shift Hamiltonian and this is the coupling Hamiltonian. So, we will consider two cases here. Case 1, 180x pulse is applied to both K and L spins in the spin echo sequence. Okay. So, therefore, evolution under Hz and Hj can be considered independently, and now as before your row 1 is IKZ plus ILZ and row 2 is minus IKY plus ILY 90x pulse. Since evolution under chemical shift is refocused at the end of the spin echo, we will calculate only evolution under Hj through the spin echo, because we have already shown that chemical shift is refocused. So, we do not need to calculate under the chemical shift again. Therefore, we will only calculate evolution under the coupling constant. Okay. So therefore J evolution, I put here picture once more here, 2IKYILZ, those of you can see it clearly, then you have that indication here as to what terms you will get. So rho 3 prime is the one, this is the result of J evolution, and I get here I had minus IKY plus ILY, right. So the first term gives me IKY cosine pi jkl tau minus 2 IKXILZ sin pi jkl tau, and you have the minus sign. This is for the K spin, and this is for the L spin, minus ILY cosine pi jkl tau minus 2 ILX IKZ sin pi jkl tau. This is under the influence of the coupling jkl, J evolution. So now I apply a 180x pulse on both K and L. So this sign remains the same. So 180x pulse takes me IKY to minus IKY, so this remains this, and what happens here, IKX does not change, L spin is applied, it takes ILZ to minus ILZ, therefore this gives me plus here. So therefore plus 2 IKX ILZ sin jkl tau, and once again here minus ILY cosine pi jkl tau plus 2 ILX IKZ sin pi jkl tau, when I apply the pulse on both spins, and this is what I will get. So simplifying this, rho 4 prime is IKY, this minus minus plus, IKY cosine pi jkl tau minus 2 IKX ILZ sin pi jkl tau, and this again ILY cosine pi jkl tau minus 2 ILX IKZ sin pi jkl tau. So now you will have to evolve under the J evolution once more after the 180 degree pulse. So now each of these terms will have to be evolved. So there are 4 terms here, there will be 4 evolutions therefore. Okay. So therefore the first term, I take away the cosine pi jkl tau part out, and IKY term has to be evolved. This gives me IKY cosine pi jkl tau minus 2 IKX ILZ sin pi jkl tau, and the second term is minus sin pi jkl tau. Now I am evolving this antiphase term. You remember the summary, 2 IKX ILZ gives me 2 IKX ILZ cosine pi jkl tau plus IKY sin pi jkl tau. Similarly for the other term, cosine pi jkl tau ILY cosine pi jkl tau minus 2 ILX IKZ sin pi jkl tau, and the last one minus sin pi jkl tau 2 ILX IKZ cosine pi jkl tau plus ILY sin pi jkl tau. So now we regroup these terms. So what I get here, IKY cosine gives me cosine square, that is the first term here, and then where else is IKY? IKY is present here, and this gives me sine and sine, this is sine square pi jkl tau. So therefore IKY cosine square pi jkl tau minus sine square pi jkl tau. And now these two terms are identical, 2 IKX ILZ, so sine cos, and here it is also sine cos. So this one is minus 2 sine IKX ILZ, so 2 cosine pi jkl tau sin pi jkl tau, and that is essentially sine 2 pi jkl tau, right. And similarly for these terms we get here ILY cosine square pi jkl tau minus sine square pi jkl tau minus 2 ILX IKZ sin 2 pi jkl tau. Now what is this here inside the bracket? That is cosine 2 pi jkl tau, IKY cosine 2 pi jkl tau minus 2 IKX LZ sin pi jkl tau plus ILY cosine 2 pi jkl tau minus 2 ILX IKZ sin pi jkl tau. Notice therefore each of the individual spins have the tau dependence in the end, and the two and magnetization components would have separated out in phase by this amount, the 2 pi jkl tau. Depending upon what the value of tau is, the phase separation between the two components of the K spin will be given by this, and it also generates here an antiphase magnetization. Okay, so this we see, and this we may not, this is not observable. If you, of course it evolves under the coupling later into observable magnetization, but if you are looking at the end of the spin echo, it is just this term which is observable and this is term which is observable. So scalar coupling convolution is not refocused at the time of spin echo. So we saw that chemical shift evolution is refocused and the coupling evolution is not refocused. This is what we had also derived by a vector picture earlier in our previous classes. Very early in the course we had actually derived this. Okay. So, we stop here and continue with this discussion in the next class.